something truly empty? Well, what is emptiness in the first place? Our way of defining empty has always been the state of having no stuff inside something. For example, if I gave you a box and you take out all the stuff in it, you're left with an empty box. But is your box really empty? Well, no, it still has air inside it. So say we take all of that out as well. In fact, we take out everything, every atom, every molecule, until you're essentially putting the inside of your box in a state called a vacuum. Meaning there's no pressure, no temperature, nothing, just emptiness. Well, there you have it. That's how empty space can get. End of story. Or is it? Well, according to classical physics, you'd be absolutely right. A state of no pressure is bound to be empty because there's simply no stuff in it. But once we scale everything down to an incredibly small level, to levels that are barely a fraction of an atom, we'd no longer be operating under classical physics. We'd be operating in a completely different dimension of physics called quantum physics. And in quantum physics, vacuums aren't so empty after all.
The quantum electrodynamic vacuum is a term used to refer to a vacuum viewed in a quantum scale, and the QED vacuum isn't empty at all. Far from it, vacuums are actually filled with particles. Small particles, big particles, particles that have no mass, but ultimately particles with energy. This is a result of a fundamental principle in quantum physics called Heisenberg's uncertainty principle. To understand this, imagine yourself in a dark room. You've got golf balls strewn all over the place and you need to figure out where they are. All you've got with you are billiards balls, so you decide to be clever and use the billiards balls and roll them in a direction you expect a golf ball would be and wait for the clap sound. If you hear a sound, then you know the golf ball is there. But wait, by throwing the billiard ball at the golf ball, the momentum of the billiard ball pushes the golf ball somewhere else. So you haven't really gained any information at all. But what if we rolled the billiard ball at the golf ball slower so that it would have less momentum or oomph when it hits the golf ball, you might say? Then you wouldn't cause the golf ball to move too much. And okay, let's try that. We roll the billiard ball a lot slower than before. But now an interesting thing happens. Since it's going so slow, there's barely any clap to tell us where the golf ball is.
It's kind of the same thing with particles. These particles are so small that simply illuminating them with light hits them with photons, these individual lumps of light. So when it hits the particle, it disturbs the particle in some way. This process isn't limited to just light. Anything we try to do to observe a particle will end up changing it in some way. Therefore, we cannot know anything for certain about a particle. We don't know its position for certain, its rate of change, its energy. Everything is uncertain. So how does this relate to vacuums? Well, the tricky thing about having a vacuum is that you end up defining certain points in space to be something. For example, in this vacuum, if I point here, then I'd have to say that the particle in this point has a position, velocity, and energy of 0. But the Heisenberg uncertainty principle doesn't allow that. In the same way that you can't assume that there are golf balls in a certain position in a dark room you've never visited before, you can't assume whether that dark room has golf balls at all. Therefore, the energy density of a vacuum is constantly changing. It's not at 0. It's something else. It's fluctuating. But how does that even work? Where does the energy come from? Doesn't that violate the law of conservation of mass and energy? Well, one thing you need to know is that the particles that appear and disappear are virtual particles. But the name virtual particles is extremely misleading since these things aren't particles at all. They cannot be measured, nor do they mathematically exist as particles. Imagine a sea of water. The water can be considered a field. Energy exists in fields. That's why we have something called an electromagnetic field or a gravitational field. Now imagine the golf balls as real particles. Dropping a golf ball in that water will create ripples in the water or in the field. The ripples can be considered virtual particles. They carry energy but do not have any mass themselves. Now what happens in a vacuum is that you no longer have golf balls, you just have water. But the quantum fluctuations I described earlier cause ripples to appear in and out of the water even without the golf balls there. Since they carry energy, they can account for the energy fluctuations I described earlier. But how do they not violate the law of conservation of energy? Well, that's because of something in quantum mechanics where quantum mechanics allows particles to cheat the law a little bit and borrow a bit of energy as long as there is an equal but opposite negative energy there as well, and they put it back really fast. Think about it like borrowing money from a friend. You can't ask for a lot of money, but you can ask for maybe a penny or a quarter. And when you take that energy, you need to give it back.
Returning to a ripple analogy, let's analyze a single ripple. When you create a crest or a rise in the ripple, you also create a trough, a depression. They can last for a short time, but eventually the ripple will in a sense die out and return to a state of equilibrium. In a sense, you can think of the crest as the positive virtual particle and the trough as an anti-particle. When the two collide, they annihilate each other.
So vacuums are actually full of these disturbances and energy coming in and out of existence. But how do we know these fluctuations are real? Aren't they entirely theoretical? Well, they were until scientists figured out a way to experiment this. Consider this. Place two thin, uncharged metal sheets really close together in a vacuum, mere nanometers apart. What you'll observe is that when left alone, these two metal sheets will attract each other and get pushed together. What's happening is that you're creating less pressure between the metal sheets than everywhere else. This is because when virtual particles appear and disappear, the only particles that can appear in that small space are the smaller ones, the ones with shorter wavelengths. Meanwhile, outside, there is no limit as to what particles can appear, so you have more of them appearing. Now, since there is more outside and less inside, you create a net pressure that pushes the two sheets inwards.
This effect has been popularized as the Casimir effect. But the Casimir effect isn't the only manifestation of these virtual particles and energy fluctuations. We also see it in the dynamical Casimir effect, or even outside in far galaxies near black holes. What is a black hole? Well, we know it as the singularity in the center of this great big black void with a gravitational attractive force so powerful it can suck in light itself. But now we know that black holes don't just suck things in, they also emit things. They emit particles, real particles. How does this happen? Well, the quantum fluctuations I described earlier explain it. So what happens is that the black hole has something called an event horizon. And it's this distance where once you're in the event horizon, you get sucked in, no escape. But if you're outside of the event horizon, you might live to see another day. Now, when particle-antiparticle pairs appear near that event horizon, there are certain scenarios where only one of them gets sucked in, while the other doesn't. So the one that didn't get sucked in now has to wander the universe forever, unable to annihilate with its partner. From our perspective, it looks like the black hole just emitted another particle. This kind of makes sense, since the particle that was emitted would have gotten its energy from the black hole. There is nowhere else it could have gotten it. And we detect this kind of emission as radiation, which is why we call it Hawking radiation. It is one of the biggest milestones in helping us understand these big black giant monsters. So we've come from studying emptiness to learning something new about one of the most incredible things in our universe. It's incredible how much we can learn by literally studying nothing at all. It really makes you think about what exactly we know. We are surrounded by amazing phenomena, and science is the study of such phenomena. It is the way we fill our universe with meaning so that empty space is no longer just empty space, but instead a beautiful cosmic dance of particles appearing and disappearing. As Miriam Kreisen once said, the
universe is not made of atoms. It is made of stories. So when is something empty? Never.